我们的下一个主题是来自华为的高级架构师约翰。约翰07年加入华为，对云计算和大数据都有非常深刻的理解。从事分布式系统的开发已经很多年了。现在目前最重要的是，他还是阿帕奇社区的这个顶级项目 HDFS 的 committer， 一直在为这个华为的 HBase 这块呢是作为一个主要的核心架构师在工作。Supporting secondary index on HBase tables have been open access for quite some time, though no concrete solution currently available in the open source version. In this presentation, we explain the high-level solution approach of Huawei's implementation, based on indexing using processors to build high-performance HBase secondary index with benchmark results and topics for future work.
Hi, good morning all. First of all, sorry to say that I cannot speak in Chinese, so I can speak only in English. Okay. Before giving an introduction about myself, I would like to introduce my team. We, the Huawei Hadoop platform team, we are mainly working in HDFS, MapReduce and Hive and HBase areas. And over the past 2 years, we have given contribution to the community by testing in these 4 particular areas, as well as contributing the issues, contributing the additional features, new features. We are mainly working with high availability area and performance area. So we are having HDFS in HDFS name node high availability, as well as MapReduce and high availability in Hive. And also we are working, we worked with the secondary index in HBase. Yeah. Coming to myself, I'm from Bangalore, India, working with Huawei R&D team in there. I'm mainly working with the HBase and Hive, but mainly active in the HBase area. So today I would like to share what we have done with secondary indexing in HBase. Yeah, before going to the details, I think quick recap on the HBase. I think whoever worked with HBase may be well knowing. I would like to just quickly go through the recap. We know HBase is the DB phase of Hadoop, and we have a master and a region server. These are the main processes, and the data is being served by the region servers. Master is the one who balances the load, and the table is split into regions. Okay, and this is a columnar storage, and data is saved as key value pairs. And we have column family approach where the related columns are grouped into column families, and one column family will be saved as one unit, while another column family into another files. And we know that it is a write first into main store, then later flush as file system into HDFS. Also, in the file, the data is logically split into smaller blocks kind of thing, and the data writing and the data reading into the HDFS and from the HDFS will happen in terms of blocks. Yeah. First of all, why we done this particular work in secondary index for HBase? As we know, there is currently no secondary indexing or indexing on the column supported as such in HBase, the current versions. We were having a requirement from the customer of doing something, because we were not reaching to the whatever the requirement of the scans, throughput requirement of the scan. So we were having huge set of data, sparse data. We were needing some kind of scans with the conditions on the column value, as well as some range conditions on the column value. But we were facing the difficulty when we were using the filter alone. When we were using the filter alone, we were getting the throughput as less, as well as there was a lot of timeouts issues, the client side session timeouts, lease expiry. I think these are some topics which is well discussed in the mailing list I have seen. Yeah, the overall solution in a very glance, if I say, the first part is like we are saving the index metadata into another HBase table itself, index table we can say, and it is a fully 100% server-side coprocessor based index. HBase already supports something known as coprocessor, which will be running at the server side. You can write some code which need to run at the server side. So this our implementation is focusing on the coprocessor based design, and it is a region-wise indexing with something called known as co-location. There will be some one-to-one mapping with the actual table region and the index table regions. The index table also will be split into regions. So there will be a one-to-one mapping, and the related regions will be co-located using a custom balancer. So it will be co-located in the same region server. So we will see the details while going into the next slides. Yeah, this is the one high-level block diagram of what is done. The green area is the part which is already available in HBase, current HBase open source code, and the other part is something like which we touched. Okay, so we can see that the first part is some extension to the client, which allows the user of the HBase to specify the index details. The indexing on a particular table need to be on which columns in that way. The second part, what is done is the load balancer, a custom load balancer. I spoke about the co-location of the regions. So this is the area which is responsible for doing that. And the third part is obviously the coprocessor implementation. So HBase allows the user of HBase to implement some coprocessor. So all the work related to the indexing and like the persisting of the index data, the usage of the index data will be happening in the index coprocessor implementation, that part. So there will be a primary user table. Corresponding to that, there will be a secondary index table where the data, the indexing details are persisted. Yeah, first we will see the table creation part. Client will be creating one table. So client is giving a request to create some table with some regions. So at that time, what will happen is, suppose actual table is having say two regions, region 1 and region 2. Always the region will be having some row key range. Like I would consider as an example A to B and B to C. That all the rows with the primary key, say row key A to B will be going in region 1 and B to C will be in region 2. If the table is created like that, then we will be creating one index table that will happen in the master side coprocessor. We will be creating one index table with the same number of regions, and the region is also having the same start and end key. The key range also will be same. And the balancer is the one who is responsible for the co-location. So wherever region 1 is going, whichever region server, the region 1 corresponding to the index table also will go to the same.
So in the previous slide, I think maybe I didn't pay enough attention. So the secondary index table, so row keys, would be different from the primary table. Right?
Yeah.
But I guess the row key from the primary table is embedded in the secondary index table, right? Because you need to provide one-to-one mapping between A, B, and C.
Yeah. I'll come to that in the index writing. That writing part it will be discussed. What row key we will use to write to the index table. I'll come to that. Yeah. So here after the table creation, the balancer will make it in such a way that the related regions are sitting in the same region server. Okay, so here I would take an example to explain the put operation, that is the write operation in HBase. So I am having a table 1 with one column family, CF1, and I am having two index on that particular table, say IDX1 and IDX2. IDX1 is on column family 1, column 1, that's I would say column 1, and IDX2 is on column family 1, column 2. So we will be having we already created using the master side coprocessor another table, index table. So that naming of the table also will be like here. That actual table name is appended with some IDX, some fixed pattern. So here I am making a put like to the table 1. The row key I am giving it as A, B, C, D, which will go to the region 1, and the data I am giving as column 1 I am giving some value as 5, and column 2 I am giving some value as Z1. So the coprocessor is getting a call at that time. So we are having pre and post operation in the coprocessor. At the pre-processing time itself, we will be putting to the index table this particular value. You can say AA IDX1 5 ABD. The index table row key is such a way selected that it will be the region start key of the index region plus the index name plus the indexed column value plus the user table row key. So the index table, that particular R2 region, if you see the start and end, the key range is AA to AD. That means it will take any row which is starting with the AA, AB, AB, AC, like that. So in order for that index region to accept the value, what we are doing is every entry into the index table, we are starting that particular with the region start key itself. That's why always it is given as AA as first part in that row key, and the second is the index name, because we are writing all the index details to the same table only. Then third obviously is the column name. So if you see for one particular index, the first two part will be static always, AA and IDX, that index name. Then the third part will be varying, which is the column value, and the last part will be the actual table row key itself. The row key itself is appended in the actual row key, because now there is no need to write any data, some dummy data will be written. Okay, so in a nutshell we can say it is one index table per user table, and all index data is going to the same index table. We can say how this index is being used in the scan operation. By the scan operation, how the index is being used. So again, the regions are collocated. So first operation in the HBase is creating a scanner, and the previous next operations will be calling next step on the scanner, like getting the next set of results. So I am creating a scanner with a condition such that C1 equal to 5. So I want to fetch all the data with the column 1 value as 5. So we have again coprocessor at the scan time. At the scanner creation time itself, we have coprocessor. At that time itself, we will create a scanner in the background for the index table also with the start row. So now here the advantage is we can fix the start row. So the start row will be again the start key of the index region AA, and the index name which need to be used, because IDX1 is the index on column 1, IDX1, and 5 is the condition, so we will say 5, and the stop row we will say 6 because it is +1. So at this step, what we are doing is we are creating a scanner for the index table at the server side. Now the actual next operation, the data fetching operation will happen from the client side, calling the next methods. At that time also we are having the coprocessor. So at the coprocessor, what we will be doing is we are calling next on the index table, the index region, index data, and from that we can remove the common part. We can remove the index start key, region start key, the index name, all the things. And the end part will be the actual user table row key, where the particular column 5 value is situated. So we got the value and we are seeking exactly to the row in the user table using the coprocessor. And then we are returning the correct value. So again for the next value there will be again one seek. So again there will be one seek. So the advantage is there is no full table scan operation. It is exactly seek to the correct row wherever the data is situated and returning the value. So the index usage will be fully at the server side, nothing will happen at the client side. So the scan operation in a very nutshell, if you can see, the coprocessor will be creating a scanner, and the index table region we can see that it is a limited data only we need to fetch. That based on the limited data, we will be doing a seek to some position, and we are returning the data from there. Okay, so initially itself we have seen that when the data is being written as we will in HBase we call the files whichever we are writing with the data as H files. So the H files are written in some units. We call it as H file blocks by default of 64 KB size. So whenever the reading is happening, we will read 64 KB one block at once. One block at once, then later another block like that. So the seeking can prevent many block fetching from the HDFS itself. And suppose some major compaction is not happened and there are multiple H files, maybe sometimes it can skip one full H file itself. Okay, and there is no need of reading any index detail back to the client and again doing a get operation, because every full operation is coprocessor based and everything is happening at the server side. So there is no network usage, nothing extra is happening. Everything is happening in the server side. Client is not very big. Yeah. When we are having this concept of co-location based and region one-to-one mapping, one big issue, one big challenge came to us is the region split. So we know that HBase having regions, and when one region is getting a lot of data and it is becoming very huge, HBase will automatically split it into two regions. So ideally speaking, we need to split the index region also at that time, because we always wanted a one-to-one mapping. So we need to do that. So we can see how we have done that. Okay, suppose we have a regions like this. One region of 0 to 9 in the user table. So ideally there will be another region 0 to 9 in the index table also. So we can see some data. I'm doing indexing on column 1. So at that time row 1 is having A, row 2 is having A, 3C, 4B, 5X, 6B, 7A. So correspondingly the data in the secondary index table is written in that way, whatever is shown. Now, ideally speaking, after the split, suppose I am taking the split point as 4, as 5. Now, the data need to be split like this. So all the data with 001 to 004 to go to one region, and 005 to 007 go to another region. So now we can see the split in the index table will be totally different, because the order in which the data is written in the index table region is not in the row key order of the actual table. It will be in the column value. So the first two entries and the fourth entry and the sixth entry need to go to the first region where the start key is, where the key range is 00 to 05, and 05 to 09 need to get the remaining data. So for that, what we have done, come to that. Ideally, in the case of when the split is happening, how HBase handles the split is for a split region. Initially, the data will not be split physically into different files. Initially, the data is just it is marked as split only. Then we will be having special readers for that, half file readers we will say, and the half file reader for one part, say bottom part, it will be first it will be created and it will be pointing to the beginning of the file, while the other part, the reader for the other daughter, daughter region that will be initially created, and it will be at first itself pointed to the middle part, and it will be trying to read it from that point onwards. So for us, what we have done is we have created a custom half store file builder. We call it as index h5 half reader, in which both the readers will be pointing to the beginning only at first. And whenever the read operation is happening, both will go from the beginning till the end, and it will see whether this particular entry is corresponding to me or not, because I know my row key range. Depending on the last part of the row key, like that 001 to 009, I can know whether this particular entry corresponding to me. If it is not corresponding to me, I will just skip that entry, and if it is corresponding to me, I will return that particular entry from the reader. Yeah. So these are the main design aspects. We'll just tell about some of the results, scanned results which we got, performance results which we got. Our implementation is not yet completed. Still we are in the process of more profiling and more fine-tuning the solution as such, the code as such. But still I would like to share, we have done the testing on a 4 region server cluster, small cluster only, with a table having 160 regions. The regions are evenly distributed into all region servers. There are no hotspots. So we have tested with 570 million records only initially. Per record size was 800 bytes. So we are having an equal condition on a column. So these are the performance results which we got. Without index, if we are fetching some 100 rows, it took around 5712 seconds, in which the indexed approach, the data are retrieved in just 45 seconds. Like that, we can see that when the resulting rows are really less, the indexing will be it will be super fast. Yeah, we were not that much okay with degrading the performance of put. We know that when the indexing is there, the put performance can go a bit on the lower side, but we were not liking it to be that much low, because the put performance was also very much important for us. So in the same cluster, with our test, now we have seen that there is almost a 10% of degradation with put performance. I think still we need to fine-tune.
So in this graph, during this test, is there a region split on the primary table?
Yeah, during that particular, whatever results I have shown, there were no splits. Only scan operation was happening.
So the question I want to ask is, since during heavy read load, people are concerned with the throughput, right? So since you need to split the secondary index table besides splitting the primary table, so I want to know the penalty.
The thing is that at that split time, we just do a marking, right? Creation of 2 daughter regions and just a marking and creation of the readers. The reading of the index detail, like that, immediately the compaction is going to happen on both the regions. So when the compaction is happening on the index region, it is like 2 daughter regions, both need to go through the entire H file. That is the pinpoint. That is the pain point there. That is the only pain point there. But the split operation as such, we have not seen it is taking much time. The split operation alone, because it is not going to split physically the data into 2 files at that time. So split operation will happen immediately. The later compaction to the normal region will take the normal time, but the index region, it may be taking more time.
Oh, you mean the actual splitting actually happens at the time of compaction?
No, actual split of the H file, like it is creating 2 H files, that will be at that compaction time, right? At that split time, we will be just marking it. We will be just creating 2 daughter regions, and both the daughter region will point to the same H file with 2 readers. So the daughter region of that bottom part will be at the beginning of the H file. The top part will be at the mid of the split key part. So in the case of index region split, both the readers will be at the beginning only, because we cannot say it as physically split. So it will be at the beginning. So both the readers need to read through the entire data.
Yeah, they just paste through
Yeah.
So people would be interested to know the penalty or the performance penalty time of the
Yeah. I think we can even test that also. The one point is that the scan performance when the actual compaction is not happened after the split. The second part is that the compaction time. Split time as such we tested. I think it was not having much impact. The split will be completed. The compaction time after that, I can share.
So there might be a temporary.
Temporarily, it can be out of it. And the only thing is that if it is not collocated, the put cannot complete as of now. As of now, in our implementation, put will not complete because the index table is not there. So we are not able to write to the index table. We just fail the put at that particular time because we want to guarantee that it is fully like when the put to the action table is happening, we need to write to the index table also. As of now, the scan time, even if the index region is not available, we will continue with the scan but the only thing is that seeks will not happen. It will be a full details.
This is because the coprocessor on the region server 1 wouldn't be able to communicate with the coprocessor on region server 2.
Yeah, there is no communication between regions.
However, this, as you mentioned, because the load balancer runs in some interval, right? When the put no longer succeeds, there should be some mechanism or feedback to tell load balancer that it is time to correct this problem.
This is a to-do kind of feature in our thing. It is open thing to support the put even if it is not collocated. So we are in the process of doing that. As I said initially, this is not a feature as such implementation. We have not completed it 100%. That's why we have not even said anything about this in the community. We wanted to complete it.
So the last question is, we mentioned utilizing, selecting potentially multiple secondary indices by looking at the filter in the scan. In your example, say column 1, column 1 and column 2. What if the filter specify both? So how do you determine? You understand what I'm saying?
Yeah.
Because
the index specification is not on the column family. It is on the column family plus qualified.
Right. What if this column family 1? What if the more than one combination appears in the filter? How do you select?
Yeah. At that time, there can be a possibility that if column 1 and column 2 both conditions are there. Suppose there is one index on column 1 and another index on column 2. That code part will select both the index together with AND condition. So what it will do is it will fetch the index detail corresponding to column 1, fetch the index detail corresponding to column 2 both, and it will be doing an AND operation to know the seek row, to which row it need to seek.
But why is it AND? The user will specify in filter OR relation.
If user is giving an or, it will be an OR operation at the index data level also. It is depending on the AND, whether AND is specified or OR is specified. And there is one more difference is that sometimes I can, as I said, I can support multi-column index also. Indexing on multiple column values. One index on multiple column. So if suppose I was having one index on column 1 and column 2, both. And if the user has specified in the scan a filter, column 1 with condition and column 2, I would go with that index on column C1 and C2, one index, so that I don't need to scan two indexes.
I think one important question is that the creation of the index table is determined, as you said, determined time of table creation or to be added later. However, the addition or deletion is a manual process, right? Meaning you're not looking at the actual read traffic to determine whether a new indices should be created. So the index creation is not a dynamic process.
Yeah, it's not like.
For example, if you create the index, either 1 or 2 on, say, column family 1 or column 1. However, when later on you found that the majority of the read or scan is that involves both columns. But there's no this combo index. Then there's no ability to break this combo index.
It is possible. In our solution, what we have given is, suppose at a later point of time, user want to create an index on an existing table itself. We have given client-side API to do that. Actually, client-side API itself is not required. I can simply say modify table in which the new index also coming. So what we will be doing at that time is, using the MR process, we will read the existing data and write into the index table also. Even that facility is added now.
Yeah, but it's an API, meaning the trigger or execution of this API is somehow manual, right?
Yeah, that is required. That is.
Thanks to introduce the next design of HBase. The HBase secondary index, I have three problems. The first, how to this design to ensure the consistency between user table data and indexed data. Is this not a strong consistency? The second is how about the putting performance? The last is whether to plan commit the source to Apache. Whether plan to commit the source to Apache.
I got the question, I think. What is your first question is, how about the consistency of the data is needed? Second question is, put performance. Put performance. Third question was, whether it is available in the open source. Here, the consistency aspect itself, as of now, what we are doing is, at the put time, at the write time, if we are not able to write to the index table, we will not succeed make the data write into the actual table, user table region as successful operation. We will revert back the data. Also at the implementation level, as you know, we are having wall also. What we are doing is the index table data plus the actual table data, we will sync the wall as one unit only. So at any point of time, even if the region crash is happening also, we are sure that it is both the data is there in one, because if the write and sync is happening as one unit only. And as of now, we are very much concerned about the 100% consistency. That's why we are, the put operation, if it was not successful into the index region, we are as of now paying. As Ted asked, we are in the process of thinking about how to add the put operation even if the collocation is not there also. That also, I think it might come soon. So we are in the process of doing that particular thing. Second question was the put performance. The put performance, initially we thought about, there is already some implementation of HBase secondary indexing like Mini, which will happen from the client side, like the index, the write into the index table will happen from the client side, both from the client side. So as we were more concerned about the put performance, cannot go that much, we went with the co-location and the region server based thing, because there is no, there should not be any extra network calls, RPC calls. Because of that, we went with this. As of now, we got this performance graph. As I said, we have not done much profiling and fine-tuning. We were during the process of implementation. So it is about 10% degradation what we have found as of now. I think we will be.
So I have some data with this performance that in my opinion, I think if you do the index for the put performance will improve the to getting performance. The put performance will improvement to getting performance. If you put for the index data, you should get the user raw data from table user table region. You should first get the raw data. So the put performance must be
So this assessment, I think, assumes some connector RFC. However, since so however, since the implementation, as Anoop said, is mostly on the server side. So there's no extra RPC involved between the client and the server. So I think your assessment.
So what extra now is that during the put, already the put operation, there will be a call from the client side to the server side. The region server will select the region and there is a write operation on the region. Means there will be one write into the mem store and there will be a write to the wall. Right? Now what is extra? Now what is extra is, anyway we know that the region for the index table is also there in the same region server. So it just need to get one more region and call one more put on the another region. So there is one more memory write, as well as there is one more wall write. In the implementation, what we have done is the wall sync, it will not happen as 2, it will happen as 1 only. So that also intentionally we have done for the put performance. So now there is only some few memory bound operations which is extra. There is no extra IO operation, there is no extra IPC codes. So that's why I think we got it like the degradation is not heavy. When we have tested, yes, you are right, when we have tested with the client side implementation which we had initially, there were it was very less performance in the put.
Oh, okay, thank you.
Okay. Regarding your third question, as such, as I said, we have not completed the implementation. That's why we were not telling to the community. Maybe with the management we can think and we can. I mean, I cannot say it as when the code can be open sourced and where it can be open sourced or something like that. Then we again, as such, there is no implementation readily happening at the community as I said. We can tell about that. Then later, as per the interest, we can.
Yeah, open sourcing, the cost of open sourcing is relatively high, especially for such an important feature. I think, see, for example, Facebook, why they almost abandoned, so they still publish their features, however, they almost abandoned the open sourcing or porting their features to chat. The reason is that the cost is very high. For example, so after this feature is published, we have some questions, right? The open sourcing must happen after satisfactorily answering all these questions, right? Because other users will have similar questions, right? So it would take some time. Go ahead.
Is there any possible to open the source, not to Apache or other?
Yeah, I think what he's saying is that can you publish the solution?
This is something I cannot really answer because I am a technical guy. There's a need to discuss with the management aspect also because this is a managerial decision, right? So maybe, I don't know. Everything I can say.
So I think the background is that Huawei is basically pushing its own data platform, right? So this would be a unique feature. So whether it's open source is, so Huawei planning to have the benefit, right?
Two quick questions.
And I will.
The first one, we need to be index the actual population of asynchronous processor. In that case, probably they can not act as a key that the second one is where we can find more information.
Yeah, and answering the second question first, I think the information will be this slide only because any other thing is not published. Okay, answering the first question, the async operation, we always somehow wanted the consistency to be there all the time because every time, all the time we need to make use of the index of the scan time. That's why we went with this approach of not you doing the async way, but doing the sync way. And maintaining the consistency because somehow consistency for us was very critical after the use case. That's why we have done it.
But index is something index you will be actually how that will impact
the thing is that if the suppose indexing on certain only part of data is got indexed, and if the other part is not getting indexed, thing is that at the scan time, maybe I need to either know this aspect, which data is indexed, which data is not indexed. So I think if the solution is at the level of changing the entire thing changing, maybe we can think of it. But as I said, what we wanted is that we should not touch the core code that much. We wanted always to upgrade to the newer version. So now the changes in the core maybe less than 10 patches, 10 places, very less. That's why we were very much not ready to touch the core code. One full thing is pluggable. So at that later point of time, it can be another implementation also can plug in.
Okay, thank you, Don. Okay.